So now we've defined differential equation and solution to a differential equation. In the last video, one important point to make is that we were offered a function and asked to check that that is a solution. And I'll periodically come back to that to remind you that that is actually going to be much easier than the task of being asked to find a solution to a differential equation. Again, that is a very broad topic that a differential equations course would devote a lot of time to, but I just want to point out a few instances where we would be able to do that without too much trouble. So to start with, look at this differential equation, dy dx equals 3x. So again, we see an example where the derivative is dependent only on the independent variable. And suppose you're asked to come up with a solution. So that means that we're looking for a function such that its derivative equals 3x. But that should be a familiar kind of question. It might be written in a way that's different from what we are used to. But here we know that if I were to anti-differentiate, then we would get a function whose derivative is 3x. And importantly, we see that when we take the antiderivative, we get this additive constant. And so when we say find the solution here, that's a little misleading in the sense that we actually get a whole class of functions, because I could let c be any value and this would still satisfy that. So sometimes we refer to this as like the general solution of this differential equation. What I'd like to take away from this example, which is going to be useful to keep in mind, is a more general idea that if dy dx can be expressed as a function of just x, so importantly, what I mean here is dy dx depends only on the independent variable. Then the nice thing about these is that you can find the solution by anti-differentiation. So that opens up a way to come up with a solution for a big chunk of differential equations. But importantly, that doesn't allow us to solve for all differential equations. As soon as we start to involve the dependent variable, we're no longer going to be able to rely necessarily on this idea of integrating. So for a very different example that does not fall into that category, let's suppose that we're asked to solve dy dx equals y. So here, the important thing is we can't anti-differentiate with respect to x like we did above, because that would say, what is the antiderivative of y, which is a function of x, when the whole point of this question is we're trying to find out what y is. So how could we find its antiderivative? So there's this kind of complexity that comes into play when we have y here. So instead, the way we can approach this is to just think about what it means about the function y. So a solution here would have to be a function such that when we take its derivative, we end up with the same function we started with. And we know that a function that has that property is y equals e to the x. So y equals e to the x, I'll point out, works. Because in the question here is above, we found a whole family of functions with that plus c. So we might ask ourselves to think of here, does y equals e to the x plus c work? We're kind of looking for an extension of this. And how do we know? Well, we check that just like we did before. Then in this case, dy dx would equal e to the x, because the derivative of c is 0, which is not equal to e to the x plus c unless c is 0, we're seeing. So we see that if I put the plus c in there, I no longer have a function that its derivative is equal to what we started with. However, trying to think about how we could manipulate y equals e to the x in a way such that its derivative still gives us the original, think about instead a multiplicative constant. So a more general solution would be y equals c e to the x. Because here, if you take the derivative of this, you always end up with c e to the x. And notice it's more general. When c is 1, we get the very specific example I came up with above. And so this is going to be our general class of solutions here. Related to that, we can make this just one step more complicated. If we want to solve now, dy dx equals k times y. Assume k is some constant. And our goal here is to try to come up with a function such that when we take its derivative, we get back the function, but times some other constant. So there's definitely some connection to the one above, the fact that you get a constant multiple of the function you started with. Again, I'm drawn to the exponential function because that fact that you still have that same function in there. But thinking about the need to bring out a constant, the way we can accomplish that is by putting that k value in the exponent. If you were to take the derivative of this function, the chain rule would bring out k, which would then give me k times the function I started with. And learning from what we observed in the previous example, I'm going to note that the general solution would be actually any multiple of what I tried above, which I can write like this. Again, if k were equal to 1, this would reduce to the example we had above, so it doesn't contradict that. And to be clear, I just want to emphasize again, the way that I'm solving these is really just thinking about the structure of the function that would need to solve this and what familiar functions I know of that have that. At this point, I want to kind of emphasize what we just found because we're going to find that this style of differential equation, dy dx equals k times y, is relevant to a lot of different applications. And even in this course, we're going to see it a lot. So I'm going to call this a fact now that you can always jump to. If you have dy dx equals a constant times y, then you automatically know that the solution is y equals c e to the kx. We're going to see what extra information we would have to know in order to find the value of c. But to be clear, the value of k is whatever that number is in the original differential equation. So we would be able to specify it like that. And then one last example, just to, again, kind of demonstrate this process of coming up with a solution, is if we were asked to solve the second derivative of y with respect to x equals minus y. And again, we are not going to be focusing in this course on very many differential equations that involve what we call these higher order derivatives. But to be clear, this is a differential equation. We would call this a second order because it involves the second derivative. But the reason I want to put this in here, because again, we can think about familiar functions. To find a solution to this, we are trying to think of a function such that when we take its second derivative, we end back up with the function, but times -1. So one thing I'll point out is that if this were plus y instead of minus y, e to the x would work again because you would get back that same function after two derivatives. So we have to veer from that a little bit to account for that negative multiplier. But if you think about our functions we deal with often, one possible example would be sine of x. If I take the derivative of that twice, I end up with minus sine. Likewise, cosine of x would work. So we can come up with some possible solutions just by thinking about the structure of that. It turns out, and I'll point out this is not obvious by any means from what I've seen here or shown, it turns out that the general solution to this would be, let's say, c1 sine x plus c2 cosine x, where c1 and c2 are any constants that we'd like. And we could certainly show that if you take the derivative of what I have underlined there twice, you get the negative of what you started with. So we would be able to show that that's a solution. But what's not obvious and what we're not really going into in the scope of this course is the fact that the only type of function that solves this can be expressed like that. But like I said, for now, we'll just say that's a fact. If you take a differential equations course, you can look at the notion of not only existence, but uniqueness of solutions.